most of the people are here. So let's continue with the afternoon session, and it's final lecture from Ash, and talking about backaction evasion, conditional measurement.
Great, so I'm going to again kind of pick up where I left off at the end of my second lecture. So I was telling you about quantum measurements in quantum optomechanical systems, and in particular the usual conventional quantum limit on continuous weak position detection of these systems. We really spent a lot of time, maybe too much time, understanding rigorously where that quantum limit comes from. And so today in today's lecture, what I want to focus on is ways to go beyond that conventional quantum limit. And these are going to be ways to do quantum non-demolition measurements in optomechanical systems, backaction evading measurements in these systems. And so I'll tell you a little bit about the same kind of setup that Keith Schwab spoke about, this optomechanical backaction evading scheme where you use a two-tone drive. And I'll really focus on an aspect of the physics that Keith didn't touch on. How do you get squeezing out of that kind of measurement? And that'll touch on a really interesting area that, again, I won't be able to do full justice. How do we think about conditional measurements? In a particular run of the experiment where you measure some measurement record, the output of your detector, how do you make use of that information? What's the theoretical framework that lets us make sense of that? So we'll address that a little bit. And then I'll tell you some things, some much more recent work coming from my group, done with a former postdoc, Matt Woolley, where we extend these ideas of backaction evasion to a system where we have two mechanical resonators coupled to a single optical mode. And the interesting thing here is this kind of backaction evasion will actually give us a strong way to entangle these two mechanical resonators. And this will actually connect with some of the things we heard about in Jeff Kimball's talks about continuous variable quantum entanglement. Okay, so where were we at the end of last class? Here is this cartoon of our optomechanical system. We had talked about conventional position detection. The motion of the mirror is imprinted on the phase of the reflected light in this homodyne current. The quantum limit, well, look, there's two kinds of added noise, imprecision noise and backaction. Because of the backaction, I can't just turn my measurement strength knob to 11. Right? The backaction would kill me in terms of this added noise. And so we end up getting this quantum limit that says, look, the added noise has to be at least as big as the oscillator's 0 point motion. So this is the conventional quantum limit. Notice I'm not using the word standard quantum limit. What does it involve? Again, weak continuous position detection. How can we do better? Well, the basic idea is we need to somehow get rid of that backaction term. So we really can crank the knob to 11, have an arbitrarily large measurement strength, make this imprecision noise arbitrarily small. And how do we do that? Well, we have to weaken one of the conditions that we put into this derivation of the usual quantum limit. Either the fact that it's a completely continuous measurement, or the fact that we're actually really measuring position. Okay, and so again, why would we want to do this? Applications to, let's say, ultra-sensitive force detection. The thing I'm really going to focus on here is if you could really do this, make one of these backaction evading measurements, that could be a really interesting route to getting some very interesting mechanical states. Squeeze states, or even entangled states. Okay, so how can we do this? Well, the first thing we can imagine doing is, let's not do a completely continuous measurement. Okay, so imagine here's my mechanical oscillator oscillating. Imagine I turn on and off the measurement strength. It's sort of hard to imagine in this situation. Imagine sending strong pulses of light into the cavity. And the idea is only make a measurement of the mechanical resonator, let's say once per period. Okay, so I make a really strong measurement at this point here, right, at this initial time t equals 0. I'm going to give the mechanical oscillator some enormous random backaction momentum kick. So mess up the oscillator's momentum. So what do? If I wait exactly one whole period before making my next strong position measurement, well, whatever that momentum mess up here was, it's not going to matter when I wait exactly one period. Okay, so this is the idea of a stroboscopic measurement. Measure once per period. For each one of those measurements, yes, there's a backaction kick associated with it. But again, because the next time I look is exactly one period later, that momentum mess-up stays as a momentum mess-up. It doesn't affect this next position measurement. Okay, so that's one approach you could take. The other approach you could take is the kind of scheme that Keith was telling us about. This idea of measuring just a single motional quadrature of the mechanics. So here's the mechanical position as a function of time. Think of that as a Heisenberg picture operator if you want. The idea is the oscillator is oscillating at its resonant frequency, omega m. I have these two operators that tell me the amplitudes of the cosine and the sine components of the motion. Okay, and the idea is if I just make a measurement of this x quadrature here, all the back action is going to go into the conjugate quadrature. So as Keith told us, x and y are conjugate observables. They have this canonical commutation relation. All the back action will go into y, and that back action won't come back and mess up subsequent measurements of x. Okay? So that's the idea of this single quadrature measurement. Yeah?
So does the stroboscopic measurement differ in that you're making really an instantaneous measurement?
Yeah, so the way I describe it here, the idea is to make a very localized in time, strong measurement. And what we'll see is this is actually going to turn out to be a gentler way of doing this. Okay? And we'll see that explicitly in just 2 slides. Okay, so this is the idea of a single quadrature measurement. You really want to just couple to that x quadrature, let's say. And again, the thing to really realize, what is this x quadrature, right? If I think about this in the Schrodinger picture, this is explicitly a time-dependent operator. Okay? So this is the x quadrature operator in the Schrodinger picture. It has an explicit time dependence. Okay? What does that mean? Well, this operator here is actually a time-dependent combination of the mechanical position and momentum. Okay, so how are we going to measure this? Right, well look, this is what we had before, our optomechanical cavity. I had x coupled to the cavity. F was the force operator for the cavity. So now, if I really wanted to measure the x quadrature, what would we like sitting in our Hamiltonian? Well, I'd like to have the x quadrature directly coupled to my detector, directly coupled to the cavity. So I'd somehow like to have a Hamiltonian, x quadrature multiplied by f, a dagger a, but that's going to be a kind of horrendous Hamiltonian to achieve. Right? Because that would, what is that x quadrature? Again, it's a time-dependent combination of both position and momentum. I would somehow have to couple the cavity both to position and momentum and modulate those couplings in time. Okay, so yeah, you could try to do that. Probably would be pretty tough. Is there something simpler we could do? Well, I like just coupling position to the cavity. We know how to do that. This cartoon does it for me for free. Right? So how can I get this coupling to turn into the thing that I want? Well, what happens if I just modulate the coupling strand? Imagine I modulate this optomechanical coupling A in time. Okay, well then the idea is, well look, I'm just going to take the mechanical position x, right, multiply it by this modulation of the coupling cosine of omega mt. So when I write x now in terms of those quadratures, right, here's the x quadrature and the y quadrature, cosine squared, right, in terms of double angle formulas gives me this. Cosine times sine gives me this. So I have the piece that I want. My cavity or detector is just coupled to the x quadrature. And here are terms that I don't want. I don't want to couple to the other quadrature. So how do I get rid of that? Well, if I could somehow time average this Hamiltonian. Right? The pieces that I don't want in this Hamiltonian, this piece in particular, that's oscillating very quickly at twice the mechanical frequency. So if I had some kind of slow detector, something that couldn't respond to things occurring at twice the mechanical frequency, I could ignore that term. Okay, so the idea now to do this backaction evading measurement, right, to just measure that one motional quadrature, I'm going to couple to position, but I'm going to modulate the coupling strand at the mechanical frequency. Which again, just going back, should remind you of this stroboscopic scheme, but doing things in a more gentle way. You're not suddenly turning the coupling on and off, you're just smoothly varying the measurements, right? Okay, and so again, how are we going to do this? What is our slow detector going to be? Our slow detector that will let us average away the bad part of this Hamiltonian is, again, just this optomechanical cavity in the good cavity limit, where the damping rate of the cavity, the kappa of the cavity, is much smaller than the mechanical frequency. Okay, so this is exactly the scheme that Keith described to us. What are we going to do in the good cavity limit? So here is my cavity resonance. The motional sidebands associated with the mechanics are really, really far away from the, the center of this resonance. The idea is to drive the cavity at both of these sidebands. And so Keith already described this. So when I do that, look, we can do exactly the same trick we talked about in the last 2 lectures. I can write my photon lowering operator in the cavity as some classical amplitude that's coming from these 2 laser drives, plus some quantum part that will be affected by the mechanics. And again, the form of drive that I'm putting in here is going to give me an amplitude which has these 2 sidebands. So omega r here is the cavity frequency, and the 2 sidebands at plus and minus the mechanical frequency give me that cosine. Okay? So now, what is my effective coupling between the mechanics and the cavity? Exactly what we've been doing throughout these lectures. Here's our original optomechanical coupling. We're going to linearize that. Right? A is this classical piece plus this quantum piece. I'm only going to keep the terms that have at most one of these D's. And so what do I end up getting? I get exactly what I want. I get a coupling between photons in the cavity, the mechanical position, and the coupling strength is modulated at the mechanical frequency. Okay, so this modulated coupling, which is sort of the poor man's version of a stroboscopic measurement, we get that exactly by driving the cavity at both those motional sidebands. Okay? And again, this is exactly the same kind of setup that we would have for cooling. For that optimal cavity cooling, you would just be driving this redutude sideband. You'd only be getting photons at the cavity frequency by absorbing phonons from the mechanics. In this case, you're driving both those sidebands. You're getting photons in the cavity both by absorbing phonons and emitting phonons. And that's good because the thing I'm trying to measure, big X, involves a mechanical lowering operator and raising operator. And what this picture also tells you is, where is the information on the mechanics going to be in this measurement? It's going to be in photons at the cavity frequency. Okay, so you're driving the cavity at these 2 sidebands really, really far from the cavity resonance. The information on the mechanics is contained in the photons that you actually get at the cavity frequency. Okay, and so just again, what is it that you actually measure? So if I just take that interaction term that we had here, I can go into the rotating frame. So go into a frame that's rotating at the cavity frequency omega r. So what does my interaction look like between the mechanical quadrature x and the photons in the cavity? It's just x multiplies, photon lowering operator, photon raising operator. I can call that the x quadrature operator for the cavity. Okay, so what's the effect of this interaction? Well, again, the cavity really is just a harmonic oscillator. I couple to the x quadrature of the cavity, that's just going to displace the p quadrature of the cavity. So I'm going to focus on the limit where let's take the dynamics of this x quadrature to be really, really, really slow. So what is this going to do? The p quadrature of the cavity will just be displaced an amount by this coupling by the value of the mechanical x quadrature, and there's a factor of 1 over the cavity damping that comes in. And so how do I measure that? Well, again, the x and p quadratures of the cavity field show up in the light that's coming out of the cavity at the cavity resonance frequency. You can measure that again in the usual way with this kind of homodyne measurement. So at the end of the day, this information on the x quadrature is in the light coming out of the cavity at its resonance frequency. We turn that into a photocurrent and sort of normalize this in a convenient way. What is our measurement signal, this photocurrent? It's a coupling constant or a measurement rate times the x quadrature we're interested in, plus some added imprecision noise, right? That shot noise that's in this photocurrent that would be there even if we didn't have the mechanics. And the way I normalize things here, this is just going to be white noise. G here is, again, the same kind of language we used before. It's this many photon optomechanical coupling. Okay, the little g optomechanical coupling times the average number of photons we have in the cavity, square rooted. Okay, so that's the way this kind of measurement is going to work. Exactly the same thing that Keith told us about. And again, as Keith also told us in his language, this physics is, I think he called it ancient physics, so it goes back to at least the 70s. And so a really nice place to see a good summary of the first descriptions of this. There's this really nice science paper from Roginski and Kip Thorne from 1980, where they really talk about how this physics works. They even give some nice schematics of things you might build to sort of realize these kinds of ideas. What I want to tell you about now is, some more recent work that we've done to add a little bit to the stuff that was known about this story even back then. And the main thing I want to tell you about is, well, how would you take a measurement like this and actually get a squeeze state of the mechanical resonator? How do I describe that? How much squeezing can I actually get? Okay? And again, I won't say much more about the experiments that Keith has done to kind of realize this kind of physics, because he gave us a really nice description of that in his 2 lectures. Okay, so let's now think about what, first of all, is the back action of this measurement. Okay, so just like we talked about in lectures 1 and 2, the mechanical resonator is coupled to photons in the cavity. It's a different kind of coupling now, a different kind of drive. The cavity still acts like a dissipative bath as far as the mechanics is concerned. What actually happens to the mechanical resonator? So now what we can talk about, as opposed to talking about the position noise spectral density of the mechanics, we can talk about what's the X quadrature noise spectral density and what's the Y quadrature spectral density. Okay, and what do we find in the presence of the measurements? I've got the measurement on, I've got this 2-tone drive on the cavity. If everything is perfect, the X quadrature isn't affected at all. So this noise spectral density has nothing to do with the coupling to the cavity. And that's the whole idea of saying, look, there's no back action from the measurement. I'm measuring the X quadrature isn't affected by the measurement. In contrast, the Y quadrature, the quadrature that is conjugate to the thing that I'm measuring, that is going to get all this nasty back action noise. So we look at the expression for the Y quadrature noise spectral density. And again, in these expressions, N equilibrium is the number of thermal quanta you would have in a mechanical resonator just from its intrinsic sources of dissipation. This extra NBA is the heating of this Y quadrature from the measurement. Okay, and what is that? That's basically just given by the strength of the measurement. So again, G here is our many photon optomechanical coupling. Kappa is the cavity damping rate. Gamma, just the same as gamma M here, is the mechanical damping rate. Okay, so if things are perfect, there's no back action, the thing I'm measuring isn't affected by the measurement. The quadrature I'm not looking at, of course, gets heated up. That's the way this measurement is supposed to work. Okay? What does it mean for things not to be perfect? Right? For things not to be perfect, well, I actually accidentally measure a bit of both quadratures. Right? So this was our actual kind of coupling Hamiltonian. We were using the fact that, look, this term here is going to average away. It's not going to play any role. What is it that lets that occur? It's being in this good cavity limit, the fact that kappa is much, much smaller than the mechanical frequency. So in general, that ratio is not 0, it's finite. What does that mean? This term here doesn't average away completely. And because the Y quadrature is also coupled to the cavity, that means you're going to get a little bit of back action on the X quadrature. And so what that means is, in this expression here, you will have a little bit of heating. So I should really replace this N equilibrium by N equilibrium plus something having to do with the back action. But the good news here is there's something very, very small in that expression. So the deeper you go into the good cavity limit, the more and more perfectly this realizes this perfect back action evading scheme. Okay, so that's good. If you really were perfectly in the good cavity limit, you're completely back action evading. But now there seems to be a bit of a puzzle here, right? So what I've told you is, look, you're measuring the x quadrature. There's no back action on the x quadrature, so its fluctuations are completely unchanged by the measurement. Okay, so imagine without the measurement, my mechanical resonator is in thermal equilibrium at some temperature. If I plotted its probability distribution in phase space, here are my two quadratures, it would just be a circle. Okay? So now with the measurement, what have I told you? Well, the x quadrature isn't changed at all. The y quadrature gets heated up. So what does that mean? If I take this circle here, in terms of the uncertainty in x, the width of this thing in the x direction, that doesn't change. But the heating of the y quadrature, well, that adds uncertainty in the y direction. This circle kind of spreads out to be a bit of a pancake. So why is this surprising? Well, if I'm really measuring the x quadrature super, super well, I'm really learning the value of the x quadrature, I'd expect to get a squeeze state where the uncertainty in the value of the oscillator's x position goes to 0. Right, so that's not happening here. In this picture here, it looks like, well, look, there's no back action. X quadrature isn't affected at all. Okay, so this, of course, is not some kind of paradox. This is just not defining the question and the problem properly. So what should we really think about? Right, so this picture here, right, where we say the x quadrature isn't affected, the y quadrature is really heated up. What are we forgetting about? We're forgetting to think about the actual result of the measurement. So in a particular run of the experiment, what's going to happen? In a particular run of the experiment, you're measuring this homodyne curve that is telling you what the x quadrature of the oscillator is doing. It's going to do, there's going to be noise in this measurement. This I is going to be doing some kind of random thing. And what is the oscillator actually doing? The mechanical oscillator is going to be in a squeeze state, where the uncertainty in this x quadrature really is greatly reduced by the measurement. And again, the y quadrature uncertainty is increased. That's the back action. So this, the mechanical state is going to be a squeeze state, but it's going to be doing some kind of crazy random walk in a way that's completely correlated with the measurement output. So the idea is, if you know what the measurement record is, you have enough information to know what the state is actually doing, and to realize that you've actually squeezed the state in the x quadrature. But if you don't have access to this measurement record, in a sense you have to average over all possible things you could get in the measurement, that's what this, fat-looking ellipse represents. Okay, so that's the picture. If you really want to see the squeezing that you're getting from this kind of measurement, you really have to think about what happens in a single run of the measurement. How do I make use of this kind of noisy measurement record I get in one run of the experiment? And that's the thing now we need to sort of develop a theory to help us describe. And so let me just quickly pause. Everyone's still on board? Making sense what I'm describing? Okay. So I'll take silence to be good. Okay, so how are we going to actually, address this problem? How am I going to understand that, look, given the fact this homodyne current wiggled in a certain way, how has my quantum system, the mechanical resonator, actually evolved? Okay, and at some level, we know in a very basic way how to think about this, right? We know that, look, if I have some quantum system and I make the usual textbook projective measurement, so I measure some observable O, I happen to get some outcome E sub n, well then I know if the state was initially psi, after the measurement, I project it onto the eigenstate of O, it corresponds to the observable that I measured. So we know from elementary quantum mechanics that when I make a measurement, I record the outcome. That outcome tells me about what the state of the system is after the measurement. Okay, so what we have to do is sort of apply that to this system here. So in this system, at the end of the day, what is it that's actually being measured? You're counting photons. Okay, it's a photocurrent that you're measuring. So now the thing I could ask is, well, look, in some very small interval of time, between t and t plus some infinitesimal dt, does my photomultiplier click? Okay, if it does get a click, well then the density matrix describing my system is going to evolve in one way. If I don't get a click, it's going to evolve in another way. Okay, and that really, in a, it might not seem like the same thing, that's really just generalizing what we already know in terms of these projective measurements. Okay, so now what we need to do is sort of take this idea, apply it in a continuous way to really address the question that we're after. So as this homodyne current evolves in time, right, just imagine all these discrete time steps as being measurements, how is my state actually evolving in time? Okay, the way that we can do that is to actually derive a conditional density matrix equation that tells me that evolution of the state of my system conditioned on what I actually measured in the experiment. So I've gone 2.5 lectures without writing down a density matrix equation. It seems like a bad time to start writing down density matrix equations. And so I'm going to try to tell you what happens without writing an equation for the density matrix. That's not to say that density matrices aren't fun and useful. And so if you're interested in this subject, I would really encourage you to take a look at this pedagogical article by Kurt Jacobs and Dan Stack, Contemporary Physics 2006. It gives a really nice pedagogical introduction to this topic of conditional quantum measurements. Okay, so why am I not going to write down a master equation for you? It turns out in this system, things are actually pretty simple. Okay, so in this system, I'm going to focus on the case where my cavity damping rate is much bigger than this optomechanical coupling big G. And in this system, things are really simple because how does the density matrix evolve conditioned on the measurement? It always stays in a Gaussian state. Okay, so I have a density matrix that tells me what is the state of the mechanical resonator. That density matrix is Gaussian. That means all I need to tell you to specify the state is what are the average values of the two quadratures, the average of x, the average of y, and what are the variances and the covariances. So all I'm going to tell you are just what are the equations for those quantities. Question?
Yeah, I don't understand why the stability is important. I mean, the Hamiltonian is still quadratic in both cases, so everything is Gaussian.
So why it's important is to get a description that what I'm doing to get the equations that I'll show you is I'm eliminating the cavity from the problem. So I just have a setup where I go from the measurement record, what is the homodyne current, directly to what is the state of the mechanical resonator. And so I've eliminated the cavity from the problem because the cavity is responding instantaneously, if you want, to what the mechanical resonator is doing.
Okay, so it changes the equation, but it doesn't change the fact that everything stays Gaussian.
It doesn't change the fact that everything is Gaussian. It changes the fact, can I completely eliminate the cavity from the dynamic? Can I just focus on the mechanical resonator? So that's correct, yeah. Okay, so what are the equations we get? So as I measure this measurement record, the state of the system is changing. The state of the system, the state of the mechanical resonator, is completely encoded in the average of x, average of y, and the covariance matrix of these two quadratures. Well, let's first look at the equation of motion that tells me how does the variance of x change. Okay, so here's the equation, the time derivative for the reduced second moment of the x quadrature. Here's the term we would just naively expect. This has nothing to do with the measurement. This is just saying, well, look, there's damping, the intrinsic damping of the mechanical resonator. This term here is saying, look, there's heating. So if I just had these terms here, this is just saying, well, look, this x quadrature variance is going to relax to its thermal equilibrium value. The number of thermal quanta plus a half. Okay, the term from the measurement is this term here. So what is this k? Well, again, I'm writing my homodyne record here. The measurement record is something times the value of x, and that something in front I've called the square root of k. And then I have this added noise, which is white noise. So this k, which again goes like the coupling strength g squared, this is telling me the strength of the measurement. So what do we get in this equation? Something that kind of makes sense. The effect of the measurement on this covariance is to cause it to decrease in time. So that kind of makes sense. I'm making a measurement of the x quadrature, as time goes on, the uncertainty, the variance in that quantity, just due to the measurement, is going to decrease. Okay, so we get a very, very simple equation for this x quadrature variance. The only new term for the measurement is this first term here. It's something that makes it go down, right? Which is what we expect. You're measuring x. You should reduce the uncertainty in that value of the x quadrature. And again, we can solve this equation to find what is the steady state. Okay, and the steady state that we get, this is the final equation here. The important parameter that tells me how strong is the measurement is this parameter c. The cooperativity, again, g, is this many-photon optomechanical coupling. And what this tells me is, as I make c bigger and bigger and bigger, as I make the measurement stronger and stronger and stronger, I make this quadrature variance smaller and smaller and smaller. Okay, so from this description, we really do get the fact that, hey, look, the measurement does tend to give a squeezing. It also tells us how does that squeezing depend on the strength of the measurement. Okay, so that's one of the things we need to know to sort of describe the state, the variance of the x quadrature. What about the average value of x? Because again, the kind of cartoon picture I gave you was, I have this measurement record. What's the state of the system? It's a squeezed state. So yes, the variance of that state is shrinking, but it's doing some kind of random walk. Right? The average value of this pancake is moving around in some random way in phase space that's correlated with the measurement record. Okay, so here's the equation of motion for the average value of x, the mean of x in this Gaussian state. Again, there should be a bar here. And so what do we find? Well, again, here's the term you would expect. It's just damped because of the intrinsic damping of the mechanical resonator. And now, here's that piece that comes from this theory that I haven't fully told you how to derive, that actually describes this physics here. So again, K, how strongly am I measuring, the measurement rate, and this C here, that's exactly the noise in my measurement record. Okay, so I have noise in the measurement record, that's this term here. That noise is causing X to move around in a random fashion. Okay, so this cartoon picture that I told you, you have a squeezed state, but it's moving around randomly in phase space, that comes out of this quantum treatment of the actual measurement. Okay, and again, the overall picture is if I combine these two kinds of uncertainties, right? There's the intrinsic uncertainty, the width of this pancake. There's the extra uncertainty that comes from this diffusive motion of the mean. If I combine those things together, I find that that total uncertainty is exactly what I would have had if there was no measurement whatsoever. Okay, so that makes us all this consistent with the unconditional theory I described to you first. Okay, so this all might seem a little bit mysterious, and again, let's not worry about it too much. In a similar way, we can write down equations for the other Gaussian parameters, the other variances that we need. The things that we really care about have to do with x, so I'll just focus on those. So these are the key equations here. The equation for the variance in the x quadrature, the equation for the mean value of x. The terms in red are the terms due to the measurement. And again, I'm kind of telling you, these come from a full quantum treatment. The last thing I want to tell you about these, though, there's also a very classical way of understanding where these terms come from. Okay, so classically, you can deal with the same kind of problem. You have some random quantity that you're trying to estimate based on a noisy measurement. So you make a measurement, you get some result. How do you update your knowledge of what that random quantity is doing? Okay, and so this is something that's addressed by basically using Bayesian statistics. And what I want to try to do very quickly is to try to convince you that these quantum equations that really tell me how the density matrix of my mechanical resonator is evolving are completely the same as what you would expect by using classical Bayesian statistics. Okay, so let me try to do this and we'll see if it works. And I should say that this is something that I probably first learned from Steve, so he can correct me if I don't get the argument completely correct. Okay, so let's jump gears completely. Let's now think about this problem completely classically. Let's just think of this x quadrature as some classical random variable. Okay, and imagine at some initial instant in time, we know that this random variable is described by a Gaussian distribution. And we know that the mean of this Gaussian distribution is x bar. We know that its variance is Vx. Okay, so then what do? Well, we pick one realization of this variable, and we make a noisy measurement of it. Okay, so I make a noisy measurement. My measurement is one realization of this random variable x drawn from this distribution, and plus some added noise. And that added noise, well, let's take that to be Gaussian as well. So the added noise, this thing I'm calling delta, it's also described by a Gaussian distribution with zero mean and with some variance, and I'm calling that V imprecision, the imprecision noise of my measurement. So now the question is, given that I've made this measurement of x, how do I update my knowledge on what the value of x is? Okay, so that's the same thing as saying, given the measurement that I've made, what's the new distribution for this random quantity x? Okay, and this is where Bayes' theorem comes in. This is where Bayesian statistics comes in. It gives us the rule for answering this question. So what do? I've made the measurement. I'm going to update this probability distribution for x because I've learned something. So the new probability distribution for x, using the information I gained from the measurement, I take that original distribution that I had, and I basically multiply it by this update factor. For each value of this random variable x, I multiply it by this quantity here, which is basically, for that value of x, how likely is it that I would have got this measurement result that I got? Okay, the conditional probability for the measurement x mes given that particular value of x. Okay, and what's nice here is, well, this initial probability, right, we took to be Gaussian. This probability here is just really the probability of that imprecision noise. That's also Gaussian. So this new probability we're going to get, it's a Gaussian times a Gaussian. This is also going to be a Gaussian. So again, this update is saying, look, I'm going to change this initial distribution to make the values of x that are consistent with my measurement more likely, the values of x that are not consistent with it less likely. When I do that, I get a new Gaussian distribution. So it's a Gaussian distribution. It has a mean. It has a variance. How are those updated? Well, here are the simple equations that tell me how they're updated. Okay, and again, V imp is basically the imprecision of my measurement. So if the imprecision of the measurement was enormous, you don't change the distribution at all. You didn't learn anything in the measurement. So these two terms completely vanish. If the imprecision was going to zero, if your measurement gave you perfect information, well then the new value for this mean would just be the value that you measured, and the new value for this variance would just be tending to zero, right? Because you have a perfect measurement, there's no uncertainty after you made the measurement. Okay, so this is just a really quick, exercise in classical Bayesian statistics. What on earth does this have to do with the kind of quantum treatment I was describing to you? So here are our classical equations. How do I connect that to what we were talking about in terms of this backaction evasion measurement? So here's my measurement record, this homodyne current as a function of time. Imagine in some little time interval from t to t plus dt, I want to make a measurement of x. So what do? I integrate this measurement record for that short amount of time. And then if I divide through by the width of that time interval, dt, and this measurement rate, square root of k, well, that's my measured value of x. Okay, so again, the measurement here, the measurement step in this Bayesian statistical problem, here just comes from looking at a tiny increment of your measurement record. So in that tiny increment of the measurement record, right, I have a measured value that is the value of the thing I'm trying to measure, the x quadrature, plus some added noise. And now we can really make a direct connection between this stuff here and the equations we have here. Okay, so this is basically telling me you made a measurement, how does the average value and the variance change? So let's look at the equation for the variance first. The Bayesian answer says, look, the variance is decreased an amount that's proportional to the original variance squared. Well, again, that's exactly what's happening here, right? Think of this as just the change that's coming from the measurement. It goes like the original variance squared. And then we're in the limit where this added noise is actually enormous, right? Because this measurement increment here, this time interval dt, is really, really short. In a really short amount of time, I'm learning almost nothing. This term here is enormous, which means in this expression here, this imprecision noise is enormous. And so I get something that's just proportional to Vx squared. It also goes like 1 over that imprecision noise, which turns out to be just a factor of k. Okay, so if you stare at the slide maybe for longer than we have right now, you can really convince yourself that this term here is exactly the same thing as this term here in that Bayesian statistics formula. In exactly the same way, how does the value, the mean value of x change from the measurement, right? Well, from this quantum formula, we had to add this kind of fluctuating term, this noisy term. It's proportional to Vx. Well, look at my Bayesian formula. The thing that I add to x bar is also proportional to Vx. It's proportional to how different was the measurement result from what you thought it should be. Right? That's what this is here. That's exactly the same thing as this noise term C of t. Okay? So the kind of amazing thing is you can do the full quantum treatment for this conditional evolution problem. How does the state of the mechanical resonator change given a particular measurement record? What you find completely agrees with this Bayes theorem. Okay, so the way that the quantum density matrix evolves is completely set by the information gain of the measurement. Okay, so maybe that made sense, maybe it didn't. Let's go back to the physical consequences of all of this. The physical consequences of all of this are that you can really get a lot of squeezing from this kind of scheme. The key equation, how does this x quadrature variance, the width of that pancake that's getting squeezed, depend on the measurement strength? Here is the important equation. C, again, goes like this optomechanical coupling squared. What's plotted here is how much squeezing do I have, right? So here's the 0 point value of this quadrature variance a half divided by the squeezed value. Here's this cooperativity parameter on the x-axis. And what this shows is, look, if you start at 0 temperature, you can start to squeeze by, I don't know, 10 times compared to the 0 point value with a cooperativity of something like 40. Even if you start far from the ground state with some number of thermal quanta, you can still squeeze below the 0 point value. And again, this plot is a little bit old. If you really ask about how big could you make the cooperativity parameter, if you think about experiments like John's experiments that we'll hear about later in the week, this cooperativity parameter can be thousands to tens of thousands. Okay, so this scheme, this idea of using measurement to squeeze, could in principle give you an enormous amount of squeezing compared to the ground state value. One thing that's also worth pointing out is like, wow, this is a really, really complicated way of getting squeezing. Do you remember something else that Keith told you about in his talk? If you really want to squeeze the mechanical resonator, why don't you just start modulating its spring constant at twice the mechanical frequency? So if you just directly started modulating the mechanical spring constant, that's like introducing a Hamiltonian like this for the mechanical resonator, a squeezing Hamiltonian. Seems like doing that would be much, much easier than this crazy backaction evading scheme and using these conditional equations. Why is this actually a better thing to do? This kind of squeezing is limited by the fact that there's a maximum amount I can have for this interaction parameter before I make the system unstable. So if you try to squeeze the mechanical resonator by doing this kind of parametric amplification, just modulating the spring constant, the best you could do is squeeze by a factor of 2. Okay, so compared to that direct coherent interaction squeezing, this squeezing by measurement can give you an arbitrarily larger amount of squeezing. Okay, so that's, I won't say too much more about this. The squeezing that I described here, it's really important to be able to follow how this pancake is diffusing around in phase space. The ideal kind of squeezing would be the kind of squeezing where you don't need access to the measurement record, that someone else could come along and look at this mechanical resonator, measure it, and tell that it was squeezed. So the last thing you normally need to do in these kinds of schemes is turn this conditional squeezing, that is the squeezing that's there when you use the information in the measurement record, into real squeezing. And all that means is use the information you have to do feedback to suppress this random Brownian motion of this pancake. Okay, and you can do that. You can use a feedback force based on the information you're getting from the measurement to turn this conditional squeezing into real squeezing. Okay, so I think I have about 10 minutes or so left. What I want to do now is change gears a little bit and tell you about a way of generalizing this scheme to maybe do something even a little bit cooler, and that is using backaction evasion measurements not to generate a strongly squeezed state, but to generate a strongly entangled state. Okay, so now we're going to be radical. We're going to change our basic cartoon where we had a single cavity coupled to a single moving mirror. And we're going to take our cavity and have both mirrors movable. Okay, so now we're going to talk about an optomechanical system where I have two mechanical resonators coupled to the same cavity. Okay? And so the idea was that for the normal backaction evasion scheme I told you about, we had a single mechanical resonator, we had two quadratures of motion. What were we able to do? We could measure this one quadrature x perfectly, put all the backaction into the unmeasured p quadrature. Well now, look, I've got two mechanical resonators. That means I have four quadratures to play with. Mechanical resonator A has an x and a p quadrature. Mechanical resonator B has an x and a p quadrature. Okay, so I could take sums and differences of those quadrature operators, right? And the x plus and x minus quadrature operator, p plus, p minus quadrature operators. Those are all good canonically conjugate quadrature operators. And now what's the idea of this two-mode backaction evasion scheme? Well, we have four quadratures to play with. In principle, I could measure this guy and this guy perfectly, having all the backaction go into the conjugate quadratures. Okay, so the idea is to measure x plus perfectly, put the backaction into p plus, measure p minus perfectly, put the backaction into x minus, and then hopefully cook up the dynamics that the nasty backaction noise in here doesn't come back and hit the things that I'm measuring. Okay, so that's the goal, right? We've got four quadratures to play with, put all the nasty stuff in the two quadratures that you're not measuring. And again, if you could do this, why would that be interesting? Well, this would allow you to measure, let's say, two quadratures of some resonant driving force perfectly. Whereas this previous scheme, you could only measure one of them. Because the one quadrature of force you're interested in goes into the one quadrature you can measure. And maybe more interestingly, if I could really measure these two quadratures perfectly, if I could squeeze the x plus quadrature and the p minus quadrature, well, that would give me exactly the kind of entangled state that we heard about in Jeff Kimball's lectures. That would give me this kind of EPR state, okay, where the positions and the momenta of the two oscillators have an incredibly strong correlation. And in fact, and again, Jeff mentioned this, if you squeeze both that x plus quadrature and the p minus quadrature, if you squeeze both of those below the 0 point value, so these things, the sum of them is less than 1, the only way to have that is to have an entangled state. You know, this is sort of like an entanglement witness for these continuous variables. Okay, so all this would be very nice to do. The question is, how do we actually do that? Okay? And so the answer is at first a little bit depressing. All we need is a negative mass for one of the mechanical resonators. So here's the Hamiltonian for the two harmonic oscillators. The mechanical lowering operators now I'm calling A and B. I'd like one of them to have a positive frequency omega. Okay, that's no problem. I'd like the other one to have a negative frequency omega. Okay? If I could do that, then writing this Hamiltonian in terms of the quadratures, it looks like x squared plus p squared, except it's x plus that multiplies x minus, p plus multiplies p minus. If I could do that, I have exactly the kind of dynamics that I want. So x plus is driven by p minus is driven by x plus. In this system of equations, well, if I'm measuring x plus, the back action would go into p plus. That doesn't show up anywhere here. In the same way, if I measure p minus, the back action goes into the conjugate quantity x minus. That doesn't show up in these equations at all. Okay, so great. All we need is some way to get a mechanical resonator with a negative frequency, and we're set. Okay, so there are proposals out there, and again, this idea has a long history to it. There are some very clever proposals for how to get negative frequency simple harmonic oscillators. Some nice work coming from Eugene Polzik and Peter Zoller, where you make use of atomic spin ensembles. There's some more recent work from Carl Caves's group, again, looking at sort of optical cavities. What I'm going to describe is a simple way to get this physics where we just generalize that same back-action evasion scheme I already described to you. Okay, so here's our cavity resonance. We have two mechanical resonators, two different frequencies, omega A and omega B. Each mechanical resonator will give me a set of sidebands. Okay, so now the idea of back-action evasion here, we're again going to use a two-tone drive on the cavity. Where are we going to put it? We're going to drive exactly in the middle of these pairs of sidebands. Okay, and so when we do that, and when we go into the rotating frame, we get exactly the Hamiltonian that we need. Okay, so with respect to these two-tone drives, one of the oscillators looks like it has slightly a positive frequency, the other looks like it has slightly a negative frequency. Okay, so the interesting thing here is there's a really easy way to realize this two-mode back-action evasion scheme in this kind of optomechanical setup. You just copy that two-tone driving scheme, you place the drive tones in between the two mechanical sidebands. Okay, so now things are going to work. And again, so this is the Hamiltonian that we get. Here's what the Hamiltonian of the mechanics looks like in this rotating frame. The quadratures show up in exactly the way that I want. And then how is the cavity coupled to the mechanics? Well, this X cavity, this is just D plus D dagger. So this is telling me the cavity photons. They're just coupled to the X plus quadrature. Okay, and again, because of this Hamiltonian here, X plus is going to get coupled into P minus. I'm going to get information on both of those quadratures. Okay, and so just really quickly, so now look, we can measure X plus and P minus without any back action limit. I can make the measurement as strong as I want. Just like before, that means I'm going to get squeezing. Here I'm measuring both of these quadratures. I'm going to squeeze both X plus and P minus. That necessarily implies we're going to get entanglement in the system. And so again, the conditional measurements is going to work the same way. Here I've drawn things in this funny kind of phase space. X plus is on the x-axis. P minus is on the y-axis. If you make use of the information in the measurement, you can actually get the error ellipse associated with this state to have an incredibly small area. Right? You really have good knowledge of both of those quantities. The only way to do that is to have an entangled state. You violate this so-called Dwan inequality. Okay, you're really generating an EPR type entangled state. Okay, so just to kind of flash to the answers. So again, the same kind of theory I described to you before, this kind of Gaussian conditional measurement theory applies here. We can calculate how much entanglement do you actually get. Okay, and so again, how am I going to quantify entanglement? There's this entanglement measure that theorists love and seldom explain, the log negativity E sub n. And so I'm not going to completely explain to you what that is. This is a way of measuring entanglement. So if I have a state that's not entangled, En is rigorously 0. The bigger En gets, the more entanglement I have. And so what does it mean to say the entanglement is 1 or 2 or 3 or 4? Let's give it an operational definition. So as we heard in Jeff Kimball's lectures, what's something you could do with entanglement? You could do this teleportation scheme that he described to us. And if I don't have a lot of entanglement, the teleportation is not going to work that well. So if you ask, what is the best fidelity you could get from a teleportation scheme, this is how it depends on this measure of entanglement, En. Okay, so if you have no entanglement whatsoever, this is just 1 over 2, that's that classical bound. As I increase the amount of entanglement, En increases from 0, this fidelity maximum tends to 1. Okay, so the results that we have here, on the x-axis is this cooperativity parameter, a measure of how strong is the optomechanical coupling. On the y-axis here is temperature. And again, you're getting entanglement values for reasonable parameters that are fairly high. So again, an entanglement value of 3 here in that teleportation protocol corresponds to a fidelity of 95%. Okay, so the upshot of all of this, that great squeezing we had with just backaction evasion measurements of a single mechanical resonator, in this case here, can give us a highly entangled state. Okay? And the only thing that you really need to get this is a large cooperativity. You don't even need to start at 0 temperature. And again, just to compare what's another way of trying to entangle 2 harmonic modes, well again, I could just turn on a kind of parametric interaction. Right? So imagine I had some term in my Hamiltonian of this form. A and B again are the lowering operators for my 2 mechanical resonators. This kind of parametric interaction will generate a 2-mode squeeze state. And again, you might think, well, isn't that much better than doing this measurement-based protocol? But exactly in the same way as the squeezing problem, there's a limit to how big you could make this parameter chi before you make the system unstable. So if you try to entangle these 2 mechanical resonators directly through this kind of interaction, the biggest the entanglement can be in terms of this measure of the log negativity is 0.7. Okay, so the upshot of all of this 2-mode backaction evasion scheme using measurement to get some kind of interesting quantum state. It can give you a high amount of entanglement, an amount much higher than you could get by just introducing a direct parametric interaction. Okay, so I think I'm pretty much exactly at the end of my time. So what I'll do is just flash up a overarching conclusion slide, which just hopefully reminds you of the things that I've told you over the course of these 3 lectures. So hopefully I've given you a sense of just some of the basics of this field of cavity quantum optomechanics, some of the basic physics that comes from the linearized Hamiltonian description, that comes from the semi-classical equations, how we think about the optical spring, optical damping, the basics of cavity cooling. And then I told you a little bit about quantum measurement in these systems, both the kind of conventional quantum limit on continuous position detection, and then some of the fun things you can do with these backaction evasion schemes. And with that, I will stop. Thank you.